Hi everyone, welcome back. In this video, we'll cover hypothesis testing using the t-test. Hypothesis testing allows us to make decisions about population parameters based on sample data. Among the various tests available, in the context of exam SRM, the t-test is most often used to test the significance of a regression coefficient. The null hypothesis represents the status quo. It assumes the parameter, here beta 1, is equal to some specific value d. The alternative hypothesis represents evidence of an effect. It states that beta 1 is not equal to the hypothesized value d. Depending on the question, the alternative hypothesis can take three possible forms. If we are testing whether beta 1 is simply different from d, we use a two-tailed test. If the goal is to see whether beta 1 is less than d, we use a left-tailed test. And if we're checking whether beta 1 is greater than d, we use a right-tailed test. In regression analysis, the most common test examines whether a predictor variable has any effect on the response. The model relates y to x through an intercept, a slope, and an error term. We often set d equal to 0. The null hypothesis, beta 1 equals 0, tests whether x has any effect at all. When beta 1 equals 0, the x term disappears. The model reduces to just an intercept plus error, meaning x and y are not linearly associated. If we reject the null hypothesis, beta 1 is not 0, so we keep x in the model. If we fail to reject it, there is not enough evidence that x contributes, and we may consider removing it. To carry out a t-test, we need to compute the t-statistic, also called the t-ratio. The t-statistic is the estimated parameter minus its hypothesized value divided by the standard error of that estimate. Beta hat 1 is the estimated slope from our regression output. D is the specific value stated in the null hypothesis that we are testing against. In almost all cases, D is 0 when testing the significance of regression coefficients. And the standard error measures how precise our estimate is. Intuitively, the t-statistic tells you how many standard errors your estimate is away from the hypothesized value. A large absolute value is evidence against the null hypothesis. To find the correct critical value from the t-distribution table, we need two things: the significance level, alpha, and the degrees of freedom. The degrees of freedom equals n minus k, where n is the sample size and k is the number of parameters being estimated. For simple linear regression, we estimate two parameters, the intercept, beta 0, and the slope, beta 1. So k equals 2, and the degrees of freedom are n minus 2. For multiple linear regression with p predictor variables, we estimate p plus 1 parameters, the intercept plus 1 coefficient for each predictor. So the degrees of freedom become n minus quantity p plus 1. The significance level alpha is the threshold for deciding whether a result is statistically significant. Common choices are 0.01, 0.05, and 0.1. Using alpha and the degrees of freedom, we look up the critical t-value from the table. For a two-tailed test, we use alpha over 2 in each tail. For a one-tailed test, we use alpha in a single tail. A t-distribution table is provided on the exam, so you do not need to memorize any critical values. Let's look at what that table looks like and how to read it. Here are the first few rows of the t-distribution table. The rows correspond to degrees of freedom, and the columns show the upper tail probability. Each cell gives the critical t-value. For a one-sided test with alpha equals 0.05 and 3 degrees of freedom, we go directly to the column labeled t sub 0.05 and the row for df equals 3. The critical value is 2.3534. Now for a two-sided test with alpha equals 0.05 and 2 degrees of freedom. Since this is two-sided, we split alpha in half. 0.05 divided by 2 equals 0.025. So we look up the column labeled t sub 0.025, row df equals 2. The critical value is 4.3027. In practice, the two-tailed test is the most common choice when assessing the significance of regression coefficients. Standard statistics packages typically report two-tailed values by default, but there are situations where a one-tailed test is more appropriate. Let's look at each case visually and talk through some examples. Here is the t-distribution, bell-shaped and centered at 0. For a left-tailed test, the alternative states beta 1 is less than d. For example, if you're modeling exam score as a function of hours spent on social media, you'd expect more social media time to hurt performance. Unless you're watching this video, of course. And if you haven't already, be sure to like, comment, and subscribe. Anyway, you'd specifically test whether the coefficient is negative. The entire significance level alpha sits in the left tail, and we reject the null hypothesis when t falls below the negative critical value. For a right-tailed test, the alternative states beta 1 is greater than d. For instance, if you're modeling the chance of passing exam SRM as a function of hours studied, you'd expect more study time to increase the chance of passing, so you test whether the coefficient is strictly positive. The rejection region moves to the right tail. With alpha of 0.05 and 20 degrees of freedom, the critical value is approximately 1.7247. The key feature of a one-tailed test is that all of alpha is concentrated in a single tail, making it more powerful for detecting effects in that direction. A two-tailed test is used when the alternative hypothesis does not specify a direction. You're simply asking whether beta 1 is significantly different from d, regardless of whether it's larger or smaller. For a two-tailed test, alpha is split equally between both tails. This gives two critical values, negative and positive t at the alpha over 2 level. We reject the null hypothesis when the absolute value of the t-statistic exceeds the critical value. Notice that the two-tailed critical value, here 2.086, is larger than the one-tailed value of 1.725 because the test applies a stricter cutoff in each individual tail. To see why, let's compare. A one-tailed test puts the entire alpha of 5% into a single tail. The one-tailed region captures 5% of the area, so the cutoff sits at 1.725. But the two-tailed test splits alpha in half, only 2.5% in each tail. To capture a smaller slice of area, the cutoff must move further out into the tail. That's why the two-tailed critical value, 2.086, is larger. Suppose your test statistic is 1.8. Watch where it falls on the plot. With a one-tailed test, 1.8 exceeds the critical value of 1.725, so we reject the null hypothesis. But with a two-tailed test, 1.8 doesn't reach 2.086, so we fail to reject the null hypothesis. So far, we've been comparing the t-statistic to a critical value. The p-value gives us an alternative approach to compare a value directly to alpha. Let's see how this works visually. Suppose the test statistic has a value of 1.9. The p-value is the shaded area under the curve beyond this point. It represents the probability of seeing a result this extreme or more extreme, assuming the null hypothesis is true. Typically in a question, the p-value will be given. For this example, the p-value is approximately 0.036. That tells us there's only a 3.6% chance of seeing a result this extreme under the null hypothesis. To decide whether this p-value is small enough to reject the null hypothesis, we compare it to a pre-chosen significance level, alpha. If we set alpha equal to 0.05, then because 0.036 is less than 0.05, the p-value falls below our significance threshold and we reject the null hypothesis. Using the p-value gives us another way to evaluate the significance of a coefficient in a regression model. Instead of comparing the test statistic to a critical value, we compare the p-value to alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis. If it's greater than alpha, we fail to reject the null hypothesis. Several SOA sample questions ask you to interpret the p-value from regression analysis, so it's important to understand both approaches. Let's work through an example of bounding a p-value using the t-distribution table. This isn't exactly in the format of a question that will appear on the exam, but it's a good example of tying the t-distribution table with p-values. Suppose you have a sample set with 9 degrees of freedom and a calculated t-statistic of 2.3. From the t-distribution table, here are the critical values for 9 degrees of freedom. We want to find the upper and lower bounds for the p-value using the provided t-distribution table, performing both a one-tailed and a two-tailed t-test. Let's start with the one-tailed test. The p-value is the probability that t exceeds 2.3 under a t-distribution with 9 degrees of freedom. Looking at the table, 2.3 falls between the critical values 2.262 and 2.821. Those correspond to tail probabilities of 0.025 and 0.01. So the one-tailed p-value is between 0.01 and 0.025. Now for the two-tailed test. The two-tailed p-value is twice the one-tailed p-value because we account for both tails of the distribution. So we multiply the bounds by 2. 2 times 0.01 gives 0.02, and 2 times 0.025 gives 0.05. Thus, the two-tailed p-value is between 0.02 and 0.05. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.